Hey guys, today we're going to be looking at composite functions. So composite functions are when you take one function and you plug it into another function. So you can write it like we have up here where you have f of g of x. So what that means is that we are taking we're taking our g of x function and we're going to plug it into our f of x function. So we're taking this g function and we're plugging it into our f function. So you can take the x, plug it into g, and then take the g and plug it into f. So that's what composite functions are. Remember, it's really important to pay attention to the order that it's written in. The order does matter. So you're plugging it into a function, and whatever order you plug it into may affect how your answer comes out. So make sure that you're paying attention to the order that you're plugging it in. So first we've got a graph here. If you look at the graph, we have that our f of x function is this curvy function. And then we've got our g of x is our more straight line function, our absolute value function here. So we're going to take some of our functions and we're going to plug them in. So we're going to take our g of x, plug it into f of x a couple times and see what we get. So I like to rewrite mine because it makes a little bit more sense to me when it's written with the parentheses instead of with that open dot. And it just kind of gets you used to how it would look both ways. So if I have f of g of 6, you could also write that as f of, and then inside of it you would put g of 6. So remember, we're going to work from the inside out, or we're going to work from the right to the left. We're going to start by taking that 6 and plug it into our g of x function first. So I'm going to look at my g and I'm going to go over to where 6 is, and that's this point right here. I have the point 6 comma 0. So that 0 is now what we're going to end up plugging into our f function. So now I could rewrite this as like f of 0, because when we plug 6 into g, we got the output of 0, and that output is now what we're going to put in our new input for the f function. And so now I'm going to come and look at f of 0. So when I come over here, f of 0 is this point right here. I've got 0, -2. So my answer would be -2. So we're taking it and plugging one into the other. So for the next one, let's use some different colors. Let's use green and purple. So I'm still going to have f on the outside, and now I'm looking at g of 4 being what I'm plugging into that f function. So let's start with g of 4. I'm going to go over to 4 and look up at my g of x function, and I've got the point 4, 2. So what that means is that now when I'm looking for f, I'm going to take that 2 that I got from that point, that y value, and that's what I'm going to plug into my next function, into the f of x function. So now I'm going to come over to 2. F of 2 is down here. It's 2, -3. So my answer is -3. Okay, so next, I guess orange and yellow. So let's do f of, I'm going to find g of 3. So I'm going to start with that g of 3. So I'm going to come over to 3, come up here, and I've got the point 3, 3. So when I look for my f function, the output of 3 is what I'm going to plug in. So still coming to 3, but now I have the point 3, -1. So my answer is -1. And we can use this lighter blue, f of, and gray, g of 7. So I'm going to start with my g, I'm going to go over to 7. Down here, that gets me 7, -1. So now I'm looking for f of -1, which is this point right here, -1, 0. So my answer is 0. So you just got to make sure you kind of work from the inside out if you rewrite it, or kind of work from the 6 to the g and then plug that into the f. So you just kind of got to think about how you're looking at it when you are going through and solving these problems. So you can do composition of functions graphically, or you could also just do it with equations. And so that's what we've got in example 2 right here. We've got two equations. We've got f of x is 3x, and we've got g of x is 2x minus 1. So if we've got f of g of 2, that would mean let's get the pen, f of, and then g of 2. So this may look a little familiar because we have done this before. We did this in a previous set of notes where we were just starting with talking about functions, and you can take a function and plug it into another function. It's called composition of functions, and so we're going to get some more practice with it today. We're going to do g of 2 and figure out what that is and plug it into our f function. So my f function is normally 3 times something. And so what I'm going to do is I'm going to take this g function, this 2x minus 1, and I'm going to plug that in. But we're also taking this 2 and plugging it into that g of x function. So we also have to keep that in mind. So I'm actually going to rewrite this, and I'm going to put that 2 in purple. And so I've got my f of x function that's in that pink. It's normally 3, and then x, and I left a big blank where x would go. Now I'm going to do my g of x function, which is normally 2x minus 1. Then I left a blank where that x would go. And now, instead of x, we're going to put 2 where x was, because that's what it's in our final parentheses there. So now we just kind of got to simplify all this down. So you got to make sure you're following your order of operations, kind of start from the inside, work your way out with the parentheses, exponents, all that kind of stuff. So the first thing I'm going to look at cleaning up is this 2 times 2. So I'm still going to have 3, and then now this 2 times 2 is 4 minus 1. Okay, then I can clean up this 4 minus 1. So I'm going to get 3 times, and then 4 minus 1 is 3. And 3 times 3 is going to give me 9. So I could say f of g of 2 is going to equal 9. Okay, and now we're going to do it the other way around. Now we're going to find g of f of 2. So we're going to switch it up a little bit. Remember how I said the order is important. You got to make sure you're paying attention to the order. So now I'm going to have g of, and then the f function is going inside of that g function this time. And then 2 is still going inside of that. So normally the g function is 2x minus 1. So leave enough space for that x. And then I'm going to put that f of x function where that space is. So normally that would be 3x. And then I'm going to put that 2 in where that x would go. So now I'm just going to clean it all up. Same as last time, I'm going to start kind of on the inside and work my way out. So 2, and then that 3 times 2 is going to get me a 6. Then I can multiply that 2 times 6, which is going to get me a 12 minus 1, which is 11. So this time g of f of 2 is 11. So like I said, the order matters. I got different answers here when I plugged them in a different order. So make sure you're paying attention to the order. And then it is also possible to plug a function into itself. So I could plug f into f, which is what we have here. I have f of, and then the 2. So f function is normally 3x, and then I'm going to switch it up and use orange here to make it a little bit more diverse, a little bit easier to tell the difference there. So then I'm going to plug in another 3x, and then in that x, I'm going to put a 2. So it is possible to plug a function into itself. And then we just got to clean it up a little bit. So starting with that 3 times 2, that would simplify down and give me a 6. And then I'm still got that outside part of that 3 times that 6, which would get me down to 18. So I could say that f of 2 is equal to 18. We're just taking functions and plugging them into other functions or plugging them into themselves. That is a possibility. So let's step it up a little bit. These were nice linear functions. Let's give ourselves a little bit of a challenge. Let's look at a quadratic. F of x is x squared minus 1, and g of x is 2x plus 5. So let's find f of g of x. And this time, we're keeping it as x. We're not plugging a number in. So when that happens, you'll probably have an x in your answer. So we're going to have f of, and then g of x. So my f of x function is the quadratic, so that's the one that's normally x squared minus 1. But instead of that x, I'm going to replace it with my 2x plus 5. That g of x is taking the place where my x would normally be. So it's going in where x would be. It's taking the place of that. So remember, if we have 2x plus 5 squared, that's where we have to write it twice. 2x plus 5 times 2x plus 5 and multiply it out. I use FOIL because that's what I was taught back when I was in high school, but you can use double distribute, the box method, whatever you were taught. So I do first times first, 4x squared, outside times outside, 10x, inside times inside is another 10x, and last times last is 25. Combining my like terms, I'm going to get 4x squared plus 20x plus 25. So I'm going to put that in where my 2x plus 5 squared was. So I'm going to get 4x squared plus 20x plus 25. And then I still have a minus 1 behind it. So I can combine those like terms, and I get 4x squared plus 20x plus 24. So f of g of x is equal to 4x squared plus 20x plus 24. Let's see what happens when we do it the other way around. So now I'm going to do g of, and I'm going to put the f of x function into the g of x function. So g of x is normally 2x plus 5, but now I'm going to take that f of x, and that x squared minus 1 is going to go where x was. So this one's a little bit nicer to clean up. We don't have to worry about squaring stuff. We can just distribute that 2. So we're going to get 2x squared minus 2 plus 5, and then combine my like terms. So I get 2x squared plus 3. So I would say that g of f, let me write that a little bit prettier. G of f of x is 2x squared plus 3. So that looks a little bit shorter than the other one, a little bit less work because we didn't have to square. Now, sometimes when you find your composite functions, if we're dealing with functions that are not always nice quadratic functions or linear functions that have domains that are all real numbers, sometimes you may have a domain restriction. So let's talk about how you could find the domain of a composite function and how that might change if you have a domain restriction with some of your functions. So the first step is to identify the domain restrictions of whatever the inner function is. Then you're going to go through and you're going to find the composite function. Then you're going to identify the domain restrictions of the composite function, so all of it together. And then when you write your final answer, you're going to include both restrictions. So that's the restrictions for the inner function and the composite function. You've got to include both restrictions there. So let's practice it. We've got 2 examples left that we're going to practice it with. So if I'm looking at example 4, we're doing f of g of x. Our f of x is x squared right here. And our g of x is 2x minus 3. So first step is to identify the domain for the inner function. So if I'm writing this as f of g of x, it's pretty easy to tell that the inner function is the one that's on the very inside of the parentheses. So when I say inner function, domain restrictions for the inner function, that's the one that's inside all the parentheses. So the restrictions for g of x is what we're looking for in this case. G of x is a nice, pretty linear function, so there are no domain restrictions. It's just going to be from negative infinity to positive infinity. Okay, 2 is to find the composite function. So let's go through and let's actually find that composite function. So if I'm looking for f of g of x, then I would start f of x is x squared. So that's going to be something squared. And that something is our g of x. So that's going to be the 2x minus 3. I gave myself a little too much room there. That's okay though. So let's go ahead and multiply that out, simplify that down a bit. So remember, we've got to write it twice and square it. So 2x minus 3, 2x minus 3. When we square it, we FOIL, double distribute, box method, however you would like to do that. I'm going to get 4x squared with first times first. Outside times outside is negative 6x. Inside times inside is negative 6x. Last times last is plus 9. So I get 4x squared minus 12x plus 9. So my composite function, f of g of x, would be that 4x squared minus 12x plus 9. So I found the domain restrictions for the inner function. I found the composite function. Now I need to find the domain for the entire composite function and see if there are any restrictions, which this entire composite function is a quadratic function. So just like linear functions, quadratic functions don't have any domain restrictions. So that means that the domain here is negative infinity to infinity. So when I write my final domain in step 4, I'm going to use a color different than yellow. That's a little bit easier. Let's use the gray. My final domain would just be from negative infinity to infinity, because when I combined step 1 and step 3, there were no domain restrictions. So my final domain is negative infinity to infinity. Or you could say x is an element of the real numbers, or negative infinity is less than x, which is less than infinity. There's multiple ways to write it. Okay, let's look at example 5. Following the same steps. So this time still doing f of g of x. If we look, our f of x function is x over x plus 3, and our g of x function is 2 over x. So when I'm looking at my composition, f of g of x, when I start to find my domain restrictions of the inside function, that's my g of x. That's this part that's over here, the 2 over x. And remember, when we have rational functions, we talked about this in a previous set of notes, we cannot divide by 0. So what that means is that that x cannot equal 0. So for my domain here, I would say that I'm going from negative infinity to 0, and then union 0 to infinity. I would have to say everything except for where x is equal to 0. So when I do my whole composition, we're going to have some type of restriction when we write our domain. So let's find our composition. Let's do that. Step 2. So if I'm finding f of g of x, so f is normally x over, so I'm going to do parentheses, over x plus 3. Okay, our x we're going to replace with our g of x, which is 2 over x. So in both of those parentheses, I'm going to put 2 over x. And we've got fractions within fractions here, so we got to do some simplifying. So hopefully you remember some of this from Algebra 2, Algebra 1, how to simplify problems that look like this. What I would do is I would take this and I would multiply the entire top by x and the entire bottom by x. So you can multiply by x over x, which is just a variation of 1. When I multiply the top, those cancel and I'm left with 2. When I multiply in the bottom, it cancels when I distribute here, so I'm left with 2. And then when I distribute here, I get plus 3x. So I'm left with f of g of x is equal to 2 over 2 plus 3x when I simplify it down. Because remember, we don't want fractions within fractions for our answers. Okay, and then our next step is to identify the domain restrictions of this new composite function. So just like our g of x that we started with, we have a fraction. We cannot have a denominator of 0, so what I'm going to do is I'm going to say that 2 plus 3x cannot equal 0. I can subtract 2 from both sides, so 3x cannot equal negative 2, and divide both sides by 3 to find that x cannot equal negative 2/3. That's where we're going to have issues in our domain. So I know that I've got the 0 from part 1 and the negative 2/3 from part 2. So both of those are going to combine into my final answer. So I'm going to say that my domain is from negative infinity to negative 2/3 union negative 2/3 to 0 union 0 to infinity. And that would be my domain. So like I said, sometimes we have domain restrictions like we did in example 5. Sometimes we don't, like example 4. It just kind of depends on what type of functions you're using for your composition. It depends on if those original functions have restrictions. So remember our rationals, our radicals, those tend to have restrictions, whereas like our quadratics and our linear functions don't tend to have restrictions. So that's it for these notes. Make sure that you get started on your assignment that goes with this, and you guys have a good day.